Faraday's law. The first thing we'll discuss is a cartoonized version of the experiment that Michael Faraday performed. And then from there, we'll talk about two different ways to calculate the induced electromotive force from that experiment. And when we set those equal, we arrive at Faraday's law in integral form. And then it's real quick and easy to convert that to differential form. So here is sort of a cartoonized version of the experiment that Faraday performed. And what we have is a loop of wire, and we're measuring the induced voltage on a voltmeter here as we take a magnetic field and pass that over that coil. Now there's some observations that were made from this experiment. The first, and maybe this seems kind of obvious, but the stronger the flux, the higher the voltage that was read on the voltmeter. So somehow the induced EMF is proportional to the flux. Well, what is the flux? Well, it's a surface integral of B dot ds. So it was observed that the magnetic field has to be perpendicular to the loop, and the less that was, the less flux there was. And of course, the stronger the magnetic field, the stronger the induced EMF. So that was observation number one. The second observation was that the more turns in the loop, the higher the induced EMF because there's more loops to capture the magnetic field. So somehow the induced EMF is proportional to the number of turns used. And the last observation is the quicker this magnetic field passes over the loop, or the more quickly changing in time the magnetic flux is, the higher the induced EMF. So the induced EMF is somehow proportional to the time rate of change of the flux. Based on what we just discussed, we can calculate the total induced voltage by experiment. So this would be the first way we arrive at that. Pulling together everything we talked about on the previous slide, the induced EMF is equal to the number of turns times the time rate of change of the magnetic flux psi. There's a negative sign here simply to enforce the sign convention. Now let's talk a little bit about the relationship between the number of turns and the flux. We can have any number of turns, but it's describing the same surface area. So if we were to integrate just over that surface, we would have just this flux term. But if we multiply the number of terms times the flux, we arrive at something called the magnetic flux linkage. And in fact, this is a longer story because each of those loops, they don't necessarily have to be the same shape or at the same orientation, and it can get quite complicated. However, if we make them all the same shape, occupying the same area, the concept of flux linkage becomes much simpler, and we can simply say that N times psi equals the surface integral of the magnetic flux. Now, copying this top equation, and we come down here, we would like to somehow in this equation come up with an N times psi. And so what we can do is move this N into the derivative. Now we have the negative time rate of change of N times psi. This is the flux linkage, and we have an expression for that. It's the surface integral of the magnetic flux. So we can simply replace that surface integral for N times psi. And then the last thing we'll do is we'll bring this time derivative into the integral and associate it with the magnetic flux density. That's because this is the only thing that can be changing with time, so let's associate it directly. And that's as far as we'll go on this page. But we have now the induced EMF equals negative surface integral of the flux of the time rate of change of the magnetic flux density. A lot of reuses of the word flux there. There's a second method that we can calculate the induced EMF, and that's Kirchhoff's voltage law. So remember what Kirchhoff's voltage law is. We add up voltages around some loop. Well, using calculus, this becomes a line integral. So if we perform a line integral of E dot dl, we will get that induced EMF. Now, I'm cheating a little bit. This is a closed contour line integral. So that point where we're measuring the voltage will be infinitely small, and that's how we can write this as a closed contour line integral. If we set these two methods equal, we arrive at Faraday's law in integral form. And each of these is simply a different way of calculating the induced electromotive force or the voltage at that little tiny gap in the loop. Now, this V equals part of Faraday's law is not normally there. I like to leave it there to remind us this is simply two different ways that we calculated the induced electromotive force at that little tiny gap in the loop of wire. We would like to convert the integral form of Faraday's law to the differential form. And to do this, we're going to make use of Stokes' theorem. Let's quickly remember what Stokes' theorem is. It's a way of converting a closed contour line integral, which will include some surface area, into a surface integral over that surface of the curls of A. So let's write Faraday's law that we just derived, which was a closed contour line integral equaling some kind of surface integral. Well, here is our closed contour line integral that we can use Stokes' theorem to write that as a surface integral of these curls. So we simply replace this closed contour line integral with this surface integral of curls. And we set that equal to our other surface integral of the time rate of change of the flux dot ds. So we have the same surface integral, the same dot ds, and we're getting the same answer. That really means what we're integrating here has to be equal. So the curl of the electric field must be equal to the negative time rate of change of the magnetic flux. That is Faraday's law in differential form. Now looking at this, let's try to visualize what's going on here. So this means if we have a time-changing magnetic field, that will induce an electric field circulating around it. This also works both ways. If somehow we could originally create this electric field around the magnetic field, it would induce the magnetic field also. Notice here, the more quickly the magnetic field is changing, the stronger the electric field. We can also see whether the magnetic field is increasing upward or downward. That would reverse the direction of the electric field as well. But the big picture to come away with is that a time-changing magnetic field will have an electric field circulating around that. If the magnetic field is not changing with time, then there will be no electric field, at least no electric field due to the magnetic field. There might be one there for some other reason, but it won't be caused by that magnetic field.